And I'll give as required, as requested, I'll give some of an overview and review talk on some progress in the last 3 years or so on applying methods of machine learning to string theory and quantum field theory and mathematical structures in general. So I wish I were there in Lisbon in person. So let me just very briefly begin with this 1984. This is a stringy audience. So I'm going to start very briefly, just refresh the minds of younger people, the younger students, that in 1984, the most important contribution to physics was this realization that 10 is equal to 4 plus 3 times 2. So this, of course, came about because of this paper of Candelas, Horowitz, Strominger, and Whitson in 85, a year after the first string revolution, when they realized that if you compactify on a Ricci flat Kähler manifold, then you get, because of this embedding, this is just group theory, of the standard model gauge group to the E8, which was realized in 1984, you get something that's very much akin to a theory of quantum gravity that also has the potential of being a theory of particle physics. So this was very exciting at the time. But at the time, the physicists didn't know what Ricci flat Kähler manifolds are. Physicists knew about Ricci flat manifolds, but Kähler was something quite new. So it was interesting that mathematicians were actually independently thinking about the same problem. And this, I like to emphasize this sort of historical perspective from mathematics, because this really goes back to Euler and Gauss, and especially the highlight of which is the Riemann uniformization theorem in dimension 1. So in complex dimension 1, the Riemann uniformization essentially says there's a trichotomy of topology being controlled by curvature. There's Ricci 0, Ricci negative, and or curvature negative, appropriate curvature negative, and curvature positive. Then this somehow governed the topology of the kind of complex dimension 1 objects they are. Of course, complex dimension 1 is real dimension 2, so these are just surfaces or Riemann surfaces. And of course, 100 years or so of beautiful work in related everything from the index theorem to intersection theory of Chern classes to differential geometry of curvature. So what mathematicians were thinking about is, how do you generalize this story, this beautiful story, which is beyond complex dimension 1? So roughly in algebraic geometry, these things are called funnel varieties, Clavial varieties, and varieties of general type. It's a proof that it's a theorem that funnel varieties or positive curvature varieties in complex geometry is finite topological type in every dimension. It is still a conjecture that the Ricci flat case is also finite in topological type, and it is also known that the general type is infinite in number. So you already see this in Riemann surfaces. In the funnel variety in complex dimension 1 is just the sphere. The Clavial in dimension 0 is just the surface of a torus. And general type are the ones with multiple holes. They're hyperbolic geometries. So it quickly became apparent to the mathematicians that to generalize story to arbitrary dimension is extremely difficult. So, but at least for Kähler manifolds, in other words, for manifolds whose curvature is controlled by single potential, this is almost possible. So, and this was the content of Clavius' conjecture in 1950s. So I won't get into details of the conjecture, but that was basically this generalization of Riemann uniformization. So of course, the famous story is, of course, it took 20 to 30 years before Yao could prove this statement, that indeed the Chern class controls this, the cohomological class of the Chern class controls this curvature. And of course, Yao was almost immediately awarded the Fields Medal precisely for this reason, because this is such an old and famous problem in mathematics for so many decades. And it just so happens that Strominger was visiting Yao in 1985, and so he had the perfect person to ask about this problem. What are these things that are Ricci flat Kähler manifolds? So in fact, I think CSHW actually named these things as Clavial in honor of this conjecture and Yao's proof. So, sorry. Yeah. So this, of course, is not the whole story. The physicists actually did a nice translation. They did a dictionary. Not only is the topology controlled by these manifolds, when you compactify the string theory on it, they also had a very nice interpretation of all of the topological invariants of these manifolds, Ricci flat or Calabi-Yau manifolds, in terms of the particles, the generations and degeneration particles. So this was the beginning of what we now call string phenomenology, the fact that you could get particle physics. Of course, what they did at the time was E6 gut theories, because the SU3 is a natural commutant in E8 to E6, and SU3 you came for free because of the tangent bundle. Nowadays, this is much more sophisticated, and I will mention a little bit about this later. So in particular, in E6 gut theories, all of the fermions, fundamental fermions, are packed into the 27 representation. And of course, E6 is less favored today. Now we talk about SU5 and we talk about MSSM and that kind of stuff. But the 27s is exactly controlled by H21 and the H27 bar by H11. And topologically, we know that the difference is exactly a half of the Euler number. This is just index theorem. So in the 1980s, physicists asked the mathematicians, and it's probably the very first time that physicists posed a precise question to algebraic geometry. And it's a very cute story. And they asked me, are there any compact smooth Calabi-Yau threefolds with Euler number plus minus 6? Well, none of the obvious ones did. The most obvious Calabi-Yau threefold is the quintic manifold in P4, and that one had minus 200 as its Euler number. And so there's too many generations. If you naively constructed an E6 gut theory, you would have had something on the order of 100 generations of particles, which is just not true. We want 3 generations of particles. So immediately, what's really nice, pure mathematicians will never do this sort of thing. So this is, I think, it's a wonderful thing about the string theory community, is that we could actually sit down and actually try to classify these things. So Yau's proof is famously non-constructive. It just showed that there exists this Ricci flat metric, et cetera, et cetera. But other than some trivial examples, there were no large classes of Calabi-Yaus. So Candelas and friends spent the first 5 years or so trying to say, can we generalize the quintic in CP4? And what they did was this beautiful thing called complete intersection CC. So these are complete intersection Calabi-Yaus, and they have this acronym, which is a CC, which is kind of cool. And all that it is a configuration of such a type, where instead of have a single projective space as an ambient space, you have multiple projective spaces in products, and you have sliced out by multi-degree polynomials. And then, complete intersection translates to certain conditions. It's not important. And then the vanishing Chern class condition also translates to certain constraints. So in this matrix notation, the quintic is just simply written as 5. The number 5, the configuration matrix of a 1-by-1 matrix is 5. There are many, many others. So Dissler, Green, and Ross and friends did things like the Chern manifold and the Tian-Yau manifold, etc. And that became an industry. What is interesting was they realized that this is a finite classification problem, and they immediately turned to and realized that this is not hand computable, and they turned to the best CERN supercomputer at the time, which is very nice. This is the first time that algebraic geometers had access to a physics supercomputer. And so they classified this to be 7,819 equivalent matrices with distribution in this way. So what's interesting to note this database is that all of the Euler numbers are negative. Okay, so this is a biased sample, because at this point, Candelas, Green, and friends already knew there's mirror symmetry, which was switch H11 with H21, and therefore map an Euler number to its minus. So this sample here, it's big, but it's biased. So they were thinking about, can we make a more balanced data set? So Candelas and friends moved on. Well, what's another way to generalize CP4? You put weights. So they classified all possible weights and also came around about 8,000 manifolds. So suddenly from one manifold that Yau immediately told Strominger, we have around about 16,000 within 10 years, within 5 years. So that's a very nice progress. And this is a much more balanced distribution. And it's actually, so far, just to mention, so far, no construction of a compact Calabi-Yau threefold has ever exceeded Euler number plus minus 960. It's possible that this is the largest possible value. Yau has a conjecture that in every dimension, the topological numbers of every Calabi-Yau manifold in every dimension, it's a finite number. But this finite number is at least going to be very, very big, as you see shortly. The most impressive work that was done in the last part of the decade of the last century is this beautiful work done by Kurs and Schake, where they based on these theorems of Batyarov and Borisov, And instead of how else are you going to generalize CP4? Well, use a four-dimensional, four complex dimensional toric variety and put a hypersurface in it. And then this hypersurface will be Clavier, provided that you don't have any toric variety, but what's known as a reflexive Gorenstein-Fano variety. I'm going to define that in a minute. So this is actually very, very interesting. It sounds very fancy, you know, what's a Gorenstein-Fano variety? All it is if you take an integer or lattice polytope in dimension, you know, n, such that there's a single interior lattice point, and such that all of the bounding hyperplanes are distance 1 from that point, then this is called a reflexive polytope. The toric variety constructed from this is known as a Fano toric variety, or Fano toric Gorenstein variety. So, okay, this is all fancy words, but this is very, very simple. Let's take in dimension 2, okay? So let's think in dimension 2, if you take a hypersurface that, you're gonna get a one-fold, and that one-fold will be an elliptic curve. So how many ways can you put a single point in a reflexive polytope? These are 16. This is known to the Italian school of algebraic geometry. People like Fano and Del Pezzo would have known about this. Everything, of course, is defined up to SL and Z. What is interesting, the next problem is already unknown. You know, you can explain this problem to a high school student, but this is an open problem. How many ways can you put polytopes in dimension 3 such that each vertex is an integer vertex or lattice vertex, and such that it's a single interior point, and all of the bounding planes is one distance away from this? It's already unknown. Del Pezzo knew the dimension 2 case in the 1890s, and you had to wait almost 100 years before Kurtz and Skaker used their supercomputer to get this next number, which is 4319. So we go from 16, 4319. Still not good enough, because if you put hypersurfaces in those, you're going to get K3 surfaces. You want the next dimension. You want four-dimensional toric Fano varieties of reflexive polytopes. And nobody has any clue what this is number. And these guys did this a tremendous work. I showed the next number is about 500 million. So that's where this number comes from. And the next number is unknown. So Skaker has a conjecture is that he has shown that the next number is at least this number, 185 billion, a very precise number. There's no theory in combinatorics with the generating function for this. This is a beautiful open problem. Anyhow, so that's a problem from mathematics. So what's this got to do with physics? Well, we've got suddenly your Clavier landscape went from 1 to 16,000 and to around about 500 million within a decade. So that's quite very impressive. Again, you see the highest one is against your 960. So I got this from the internet. I love showing this thing. So the age of data science is actually much earlier than you think in mathematical physics and in theoretical physics. You know, this is what we do these days. You know, we download data from the cloud. So if you want to know more about this story, sorry. So here's I try to summarize the history of all of this in this book, which hopefully would appear this year, just to emphasize that now so many parallel groups still just data mining the Kreuzer-Skaker data set. Okay, so this is a plot of the distribution of the Hodge numbers of the Clavier threefolds. Okay, so anyhow, let me continue just to make sure that we're not searching in a null set. So there have been some success, you know, just because we have big data, it doesn't mean that we can actually construct anything that's akin to the standard model, right? Maybe you just get nothing. So reassuring works in the last at least 15, 20 years. You know, the one especially in the Penn group that I was involved with Volker Braun, but over at Tony Pantev and Bouchard, and we showed, well, actually you can actually construct a bundle to give the exact MSSM spectrum from this kind of construction. There's a nice work by the Oxford collaboration where they showed the probability of hitting, you know, an exact MSSM spectrum from this particular construction is about 200 in 10 to the 10. And this is very much in line with this earlier beautiful work in the late 90s by Dieter Lust and friends, that, you know, in type 2A, you also get about 1 in a billion of getting some kind of an exact spectrum kind of estimates. So I'm agnostic, but Philip Candelas is still, he thinks there's some kind of a selection mechanism. There's a geometric selection rule which tends to find universes which are akin to us. This is still an open problem in physics and an open problem in mathematics. So meanwhile, this whole program was very nicely distracted by the mid-1990s, because you see, this program was, the height of this was, mid-1990s. The reason for that, of course, as is well known, there's been a complete explosion of the landscape of string theories, right? With every possible, or all of the seminal works, that the Clavier landscape, as big as it is, 500 million is big data even by today's standards, is just a tiny corner of all possible scenarios that one can do. So in some sense, string theory trades a very hard problem, the quantization of gravity and the incorporation of particle physics, by another very hard problem, which is how to write for the right compactification. That's the vacuum degeneracy problem. In a way, to me personally, I find the second problem much more interesting, because this gives more dialogues with mathematicians and computer scientists in every branch of other, in a scientific endeavor. So just to summarize, where do we stand in the past 10, 15 years? Well, the good thing is that there have been large collaborations of physicists, computational mathematicians, the SAGE project, and you name it. And all of these people have compiled, a lot of things that, a lot of my research is just trying to access this data and compiling this data and putting it out there. And it's all free, and typically about 1 gigabyte to 10 gigabytes of data. So it's nothing overwhelming. And I highly encourage the young students to just download this data, just Google them, download them, and play with them if you can't sleep in the middle of the night. So that's the good thing. The bad thing is that any generic computation involved in this is hard in the complexity sense. So if you talk about, if you want to do toric varieties, the dual cone algorithm is an exponential running algorithm. If you want to do triangulation of toric varieties, it's an exponential. The most difficult bottleneck to computational algebraic geometry is the establishment of the Grosvenor basis. So basically, the reason why why algebraic geometry, this field of algebraic geometry, can be put in the computer is because people like Dan Grayson and Mike Stillman and Hao Shank have created these things like Macaulay 2 and other people called Singular in the German collaboration, is to just try to compute, can I just throw in a polynomial definition and you give me a cohomology of this particular variety, right, for example. But the problem is the bottleneck is the Grosvenor basis, which is a generalization of Gaussian elimination. And Gaussian elimination is n log n complexity, but Grosvenor basis is double exponential in the degree of the variety. So it's very quickly, it's just going to take longer the age of the universe. The quintic can be done. You can, I can type in the generic quintic on Macaulay 2, and I can compute all its cohomologies that's needed. But that's, that's one quintic, right? More complicated than stuff, it's almost impossible. So if you want to put all this data and just do it the hard way, it is impossible to sift through. You have to do lots of nice tricks. So a natural question is, can we borrow techniques from the big data revolution that's just started in the last, I guess, 5 years or so? So here's a wild question. Which I guess got me thinking, which is, a typical problem in string theory and in algebraic geometry for that matter, is that you have some kind of integer tensor and you want to spit out some kind of integer output, whatever it is. This could be cohomology, this could be, Hodge numbers, intersection numbers, or whatever it is. So a natural question is it possible to come up with sufficiently clever AI that will learn this process? Okay, so that's the problem I was thinking about in 2017. And I was surprised to find that experimentally that this was actually possible. So so for the rest of this talk, I'm going to try at least speculate on why this is possible. It's very interesting that 2017, my friends are independently thinking about similar kind of problems. So you see this beautiful works of Sohn-Krefel, Well, and Carifel. This is the Northeastern collaboration. We're thinking about different, similar lines of how to use machine learning to try to solve hard problems in the physics. Because of my background, my motivation, main motivation, is to see how does machine learning help with algebraic geometry, right? So it's interesting for this audience to see what this is kind of fun, right? The first string, so these are annual conferences. You can see kind of progress. 86 was the first strings, right? That's after the first string revolution. 2002 was the first string pheno, string pheno. String math didn't come about until 2011, right? And there was a precursor of the 2006 of the string vacuum. This is an NSF project I was involved with, and Keith Dennis was heading. And then in 2014, Well, okay, so this is probably my proudest contribution to string theory, is that at least I made sure that in the SIAM, in the industrial mathematics session, I have like thousands of people doing that. There's a theoretical physics session. But in 2017 now, Fabi Ruler and my friends Halverson and they're now, this is an annual conference of string data. So you see, this is very interesting that this is becoming part of the standard of this community. So just very briefly, and I apologize for any experts in the audience, the prototypical question that got me thinking was, what is machine learning? So here's machine learning in 1 minute, right? So I want to write these digits, and I want to map this to this. How do you do it? Well, a mathematician will say, well, let's find some topological invariants about this, Morse functions, whatnot. But that's extremely inefficient. It's doable, but it's inefficient. What Google does is to take some database like NIST, and then just do this association rule, right? So these have been labeled. And I believe, and NIST, of course, goes back to the 1960s. So I think some poor graduate students over the course of 30 years or so, teams of graduate students, large parallel clusters of teams of graduate students have been labeling this data for about 30, 40 years. So now we actually have this data. But what this data is, if you look at it individually, this is a typical NIST entry is a 28 by 28 RGB valued tensor or matrix, if you wish. So then what you do is you essentially do regression. So what I'm going to focus in this talk is a supervised machine learning, where we have the data, have this label, when this picture goes to number 3, this picture goes to number 5. Of course, there are many, many rubrics of machine learning. There's unsupervised machine learning, where you try to let the computer go to search for patterns itself. There's reinforcement learning, so on and so forth. But supervised machine learning is one of the core chunks of this community. And what they do is, well, because you've given me such clear labels, can I find shortcuts to do this? Well, let's try to see. So if you have a single neuron, well, what's a single neuron? A single neuron is just some nonlinear activation function. And then you minimize some standard deviation or some cost, known as a cost function. And then you do these parameters, and you try to find the optimal solution. And what you do is you feed in some data that does this, and you call that training data. And then you take, once any of these weights about these parameters in your theory are rigid, you check it on some validation data. It's extremely important that your training data and your validation data are different. Otherwise, you just overfit it, right? But if you look at this, well, this is just regression. From Stats 101, this is just regression. Absolutely. A single neuron is just nonlinear regression. There's no magic there. The entirety of the complexity of neural networks is, this thing. There's this standard book by Bengio and friends, which is sort of the Bible of machine learning, and they call this connectivism is the emergence of complexity, which I think is a wonderful way of putting it. What you do is, instead of having a single activation function, you link them up in some complex graph, and then it's this interconnectivity of nonlinear regression that does the trick. And this can be put in a precise way. So just a few definitions. This way, so this is called a multi-layer perceptron or a feed-forward neural network, because my graph here just goes forward. I mean, of course, they're feed-backward ones, but I'm not going to use them here. So the feed-forward neural network is just something that's layered, right? And the number of layers is roughly called the depth. The number of neurons per layer, or the maximum of the number of neurons, is largely called width. So deep learning is just simply when this depth becomes very, very large. And now there are what's called universal approximation theorems. There are various statements, which essentially says that given enough width and enough depth, you can approximate any function. Okay, so I mean, that's essentially, you can prove that by Taylor expansion. So that's the fundamental reason for that connectivity leads to the emergence of complexity, is because we have Taylor series of very complicated functions. And this is, again, I want to emphasize, this is why also it is extremely important to cross-validate, to validate on a data that you're not training on. Because you can see if each neuron has like 100 parameters, this whole network can end up with hundreds of thousands of parameters, and that could be more than your data point. Right? So why has this become so, why has this taken off in the last 5 years or so? this kind of structure would be unthinkable by 2000s. Kreutz and Skarke could not possibly do it because even their supercomputer could not have enough processing power to try to optimize 10,000 parameters. Got to solve partial derivatives, a Jacobian of 10,000 by 10,000. It's not possible. So one of the breakthroughs was what's known as AlexNet, which is done by this guy called Alex, Lishenko. I'm blanking out on the name. But in 2013, realized that if you use GPUs in the modern personal computer, you have enough GPUs, which is just good at tensor transformations. And that was enough to classify images, a huge problem with image classification, to extreme efficiency. So basically, the reason that machine learning has taken off in the last 5 years or so is because now each of us, we have access to a supercomputer because of gaming. The gaming industry has brought us GPUs. So how is algebraic geometry fitting into this? Well, what got me thinking in this in 2017 is, well, here's a SISI configuration. I started with SISIs because this was my bread and butter. It doesn't matter. I'm not gonna bore you to explain where this configuration comes from. I can read it. This is some product of P1s defined by multi-degrees, blah, blah, blah. It doesn't matter. And then I try to do its computation. Say, for example, I want to compute H11, the Hodge number, and it turns out to be 8, whatever. And I know how to do it. And this wonderful book of Hoops, the Beast Theory, tells you how to do it. You chase exact long sequences until you're blue in the face. I spent all my graduate years doing this, and I can't do it anymore. It makes me want to cry. So at the end of the day, despite all of that complexity, remember that computation is a double exponential complexity problem, right? But somehow clever people have, over the years, have gotten this to be number 8. But how is that different from saying that this picture should be associated with a number 8? Where this picture I've just basically plotted, I've put 1 as green and 0 as purple, whatever. And so you do cross-validation. And I didn't think at the time that this was going to be possible. Right? Because if so, then there's some underlying pattern here about a computation cohomology, which we just simply don't know about. But surprisingly, this was doable. So I tried some initial experiments, and then with my student Kiran Bole at Oxford and my friends Jajala Mishra, this has been improved by 2018-19, it was already getting this is a 20-channel classifier of just feeding in matrices and trying to predict what it is. Okay, there are improvements, and I want to emphasize on this one by Urban and Finatello just in July last year. They used this fancy convolutional network, and they were able to get 99.9% accuracy on predicting the Hodge number, which I think is great. It's not 100%. I'm going to mention the difference between 100% and 99% in a minute, which is kind of interesting. But the key point is that this computation takes seconds as opposed to potentially much, much longer. I know for the SISI data set, you didn't take the age of the universe, but it was still a very hard computation that required supercomputers to do. But here, you can just try to spot the pattern and trying to predict what this is. Well, what about other problems, right? So, what about distinguishing elliptic fibrations? That's another hard problem. We have the data for that. So with Sonju Lee, we try to say, well, is this possible? So here's an interesting plot. We try to train at 30%, and this is again within SISIs. I try to see, validate on the remaining. So you can see up to 20%, it was struggling. This large arrow bars means that the accuracy was going crazy. But by the time we'd reached 30%, your neural network has begun to spot a pattern. And by 40% training data, you're almost at 100% accuracy. We're talking about over 99%. And of course, this is extremely useful because instead of trying to use all these fancy theorems to decide whether something is elliptically fibrate, which is obviously useful for F theory, you can just now guesstimate at a few seconds on your laptop and say, oh, okay, with 99.9 confidence, this manifold is an elliptically fibrate manifold without going through the rigmarole. So this is kind of nice. So in the last two to 3 years, the community has really taken off with lots of wonderful. I can't possibly summarize all. Just some highlights. Euler used genetic algorithms for compute bundle cohomology, and Halvorsen, Nelson, and Long and friends have used this, of course, on the big KS data, right? Because the KS data is now out of reach of conventional computers. In fact, I had a joint NSF grant with Nelson and Jajala and James Gray to use the the Azure platform of Microsoft to mine the KS data. And even that could only get us to just a bit above the tip because there's just so many of them. So it's a very meaningful thing for the Northeastern collaboration to start mining this KS data. And there's other stuff I won't bore you with all the details. Another wonderful thing is this paper of Brody, Konstantin, Lucas, where they trained their neural network to try to compute cohomology in regions of moduli space, okay? Because we know cohomology jumps. And very quickly, they were able to get 100%. Now, if you get 100% consistently, that's a conjecture. So they were able to do this and then formulate a conjecture about what the analytic formula for the line cohomology is. And then they sat down and then it was actually correct. So this is a very nice thing to do. There are more, I can tell you all these great success stories from various of our friends. And I like to point out some of these really nice works in the last 2 years of Hashimoto, Halvorsen, Van Churin, and Melo Koch and friends, who are proposing something even more fundamental, which is it possible that fundamental laws of physics are themselves interpretable as neural networks? Okay, I think this is a wonderful idea. That Hashimoto, for example, rewrote the ADS-CFT dictionary in terms of a neural network, a Boltzmann machine, where you can produce, the bulk geometry by studying the boundary information. But what got me thinking, on the other hand, is let me see how I'm doing on time. Okay, I'm good. So what really got me thinking is, well, this seems a bit strange that algebraic geometry is so amenable to machine learning, this kind of paradigm. Luckily, string theory in this community, we like algebraic geometry. We made friends with them back in 1985 when Strominger was visiting Yale. So what about other branches of mathematics? Could we establish a sort of comparison between different branches of mathematics to see whether a generic problem in different branches and how they respond to this kind of paradigm? So let's try something crazy, right? So what about representation theory, which is probably the physicist's next favorite branch of mathematics? So, well, representation theory basically goes into two classes of problems: continuous groups and discrete groups. So with the number theorist Min-Young Kim, I was trying this following experiment. If I give you a finite group is completely defined by the Cayley table, its multiplication table. And a Cayley table is a Latin square. It's a pseudocode, no repeated columns or rows. But not every Latin square is a Cayley table, right? You need to build in associativity. So can I train 100,000 of Cayley tables, with permutation enhanced, and then make the machine just pick out binary classification, the ones that are Cayley? And that was great. And that turned out this problem was doable to 95. So I'm reporting two numbers. The first number is naive precision, just how many percentage agreement. And the second number is chi-square. I also have to make sure I don't have that many false positives or false negatives. What is more striking, okay, so fine, maybe it's kind of learn some kind of permutation rule. What is more surprising is the following. Is it possible to look at the Cayley table and recognize this finite simple group? And of course, this problem is extremely difficult. The classification of finite simple groups took over 200 years, and it's only been completed in 2008 in the last definitive volume of Gorenstein. And but now it doesn't matter. Let's just throw in 100,000 Cayley tables. Of course, I couldn't do it. We only took 100 groups, shuffle them, and then what is surprising is I was able to use a support vector machine. There's no neural network. So what a support vector machine is, you give point clouds of data, and then it tries to find a hyperplane that separates them. It seems, at least this is a semi-conjecture we have, and we need to do more data for this. it seems that if you plot the space of finite groups, the simple ones are separated from the non-simple ones. And if that's really true, this would be quite a novel way to do representation theory. It's kind of crazy. It's an infinite dimensional space, and you take the Cayley table, you flatten it into an infinite dimensional vector, and here's the proposal, at least from small, from the first 100 groups or so. It seems that the Cayley table in this vector space, the simples and non-simples are actually separated. I have no idea why, and I will talk about this in a minute. Why? What it means to say I have no idea why. And other things, what about Lie groups? With Shailesh Majumdar and Han-Yu Chan, we're doing other. Can you tell just by feeding in weight vectors of Lie groups? Can you tell how long your irreducible representation is? And that also you can see reaches fairly high accuracies as well. And yeah, so representation theory, good. Algebraic geometry, good. What about combinatorics? So here there's a paper in last June that I had with Yao, which is, well, our original motivation was to study the graph Laplacian. There is a notion of discrete Clavier manifolds, and that was our original motivation. But while doing this, we got thinking, well, why don't we just take random databases of graphs, of finite simple graphs, to see whether you can detect whether it has hard problems, right? Whether the graph has any cycles, has any plane. Here again, the structure is very, very simple. You feed in the adjacency matrix of the graph. As long as your data is representable by tensor input, and you have a definitive output, whether it's a categorization problem or a regression kind of problem, you have this data. And once your data reaches the size of 10,000 or above, then you're fairly confident that we have a good chunk, and you can play with this. So I played, so okay, fine, these have some numbers, but note that these numbers are getting lower. So combinatorics seems a little more difficult problem than representation theory and algebraic geometry. And here is two problems which got me disturbed in the beginning, which is, what about detection of Hamilton cycles versus Euler cycles, right? So the Euler cycles is the ones which traverse every edge once, right? This is the famous Königsberg bridge problem. The Hamilton cycle ones is ones that traverse every vertex once, and that's the famous traveling salesman problem. The Euler cycle problem is known to be a polynomial time algorithm. The Hamilton cycle one is NP complete. So the traveling salesman, and yet they performed a roughly the same order. Interesting. Why is this hard problem performing as good as an easy problem? Well, luckily, one finds that stochastic solutions of the traveling salesman, if you don't want to find an algorithm which gives you the minimal path that takes every single point exactly once, but if you want to say, well, with 90% confidence I can do this, then there are hosts of papers that stochastically says that this is also a fairly simple problem. So this is, because after all, we are just doing statistics here. So what would tend to break it? Here's the question. Well, primes. Right? Finding patterns in primes will be difficult. So we try, sorry, this hard, I don't mean hard. I don't mean hard in the complexity sense. I mean hard as in difficult. So here's a wonderful problem, right? You feed in the neural network that goes through 2 to 3, 2, 3 to 5, 2, 3, 5 to 7, blah, blah, blah. Can you predict the next one? And very quickly you'll find it's not doing anything. You're breaking even to random guess, which is good and bad. It's good. It means that somehow the structure of mathematics is preserved. The bad thing is that I can't break every bank in the world, and I can't become an instant billionaire, because if I can do that, I can start factorizing primes this way. So it's kind of reassuring that this class of problem is not doable. And so too, you would expect hard problems in analytic number theory, like the BSD conjecture. However, more recent experiments with my students at Hurst and Toby Pitkin, and also with hardcore other arithmetic geometers, Kyu-Hwan Lee and Tom Oliver, we've been doing things like in arithmetic geometry. So this is a class of problems where, so basically, Riemann hypothesis is in this class of number theory problems, but things like Fermat's last theorem is in this class of problems. So there, if you try to learn, simple problems like properties of arithmetic curves, if I give you an elliptic curve and I define over some number field, and I want to know, can you tell me what the rank of this elliptic curve is? What are properties of this L function? And recently this is becoming much more of an industry in physics because of the moonshine conjectures. Well, this one is achieving extreme precision, very, 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 very good precision. So in some sense, arithmetic geometry, even though it's usually classified as number theory, is closer to algebraic geometry than it is to number theory, in traditional hard arithmetic problems. That's kind of interesting. So here's well, since I have time, good, I'm being conscientious on time. I have 17 minutes, which is good. Or I'm okay, right? I have like 5 more minutes. Just.
Yeah.
Yes? Yeah, okay, good. What about metaphysics? I don't mean metaphysics as in metaphysics, I mean meta-mathematics. Is there linguistic structure to the archive, right? So there's a paper by Mikolov. Oh, by the way, Alex Lishenko and Mikolov, they're all hired by Google now. This is why Google DeepMind is so great. They scrape out all these people. Mikolov had this wonderful idea of mapping contextual text of words, sentences, into a vector space. I want to get into the details, but essentially for physicists like us, or mathematical physicists like us, he basically minimized a partition function of distance. So word frequency is not good enough to tell you what text you're reading, but if you minimize this partition function, which also takes in the distance, the relative distance of words, you can map this using a neural network, which he calls word2vec, into a vector space. And this vector space has a structure. And this is why, when you type in Google searches, it's because of Mikolov, who was hired in 2013 by Google. If you type something, it auto-completes because he knows what's the probability of the next likely word is in this vector space. So what we did with Jajal and Nelson in 2018 was we downloaded all of the titles of the 6 different categories of archive. Okay, so if you look at the word cloud distribution of the 6 archives, have TH, have PH, you don't see much difference. The word model, fine. GRQC had the word black hole, which is kind of good, whatever. And then we ran it through into Word2vec. And this now, having rigid constructed this vector space, you can do interesting syntactic structures of what we call science. So one thing that really got me, well, each word is now a vector, right? You can add vectors. So you can see things like bosonic plus string theory is equal to open string. So you're beginning to see the emergence of semantics from syntax alone. This is kind of interesting. My favorite one is this one. String theory plus clavial is equal to M theory plus G2. I mean, of course, string theory is a 200-word vector of whatever entries, and you add this vector plus this vector. The closest matched vector is this 2, which actually contextually is actually correct. So this is kind of nice, and what is interesting, I won't bore you with this, is we tried this with Vixra, the crazies archive, right? They didn't have this structure. This is just title, right? Just from title, right? We want the full text, but we don't have technology to do this right now. But something like the Crackpot archive, they don't even have their own consistent syntax to be what we call science. Whereas archive, even at the title level, we already do. So this is actually I couldn't convince Vishnu and Brand to drop everything they do to keep on working on this. We ran out of steam. But in 2019, this Nature paper of Chitoyan did exactly the same thing to material science, and they took all abstracts. There's more information, 3.3 million abstracts, and they were able to predict hundreds of new reactions that are more efficient than what they have now. So this is already, they're letting Word2vec, they're letting a neural network do science, essentially, in a way. So that's kind of fun. So good, I think my time is coming to an end. So let me just summarize. Well, this kind of paradigm is clearly useful for physics. First of all, you want to do classifications and conjecture forming for solution. You want to find solutions. But also you want to do estimates, guesstimation, predictors. If you can't do the Korteskaka 500 million data points, but maybe I can do it in under a month running time if I can just estimate maybe 90% of streamback you are likely to be here or there in this particular island or not. For math, surely this is also very, very interesting. Of course, you can do stochastically, you can do NP hard problems. But you can also form new conjectures. Once your neural network, especially in a supervised learning context, If your conjectures can reach 100% consistently, do you have a conjecture? Then try to prove it. Right? And then what's also interesting to me is that you kind of get somewhat of a hierarchy of the difficulty of machine learning algorithms with different branches of math. I'll try to summarize in this paper, which I just put out yesterday. It's kind of as you would expect. And I think algebraic geometry over the complex numbers is very good, because any problem in algebraic geometry over the complex numbers comes down to finding the kernel or the co-kernel of an integer matrix. Right? This is the entirety of the problem in this field, is about finding the kernels and co-kernels of integer matrices. And that's something that neural networks are more or less good at. And that's why this field is very much amenable to this kind of analysis. So nothing much more to say. There've been over the last 2 years, this is just last 18 months alone, there've been all these papers in Nature and Science of various, there's SciNet, which by Reno and all, which try to, this is kind of fun. They build this neural network called SciNet, where they feed in the positions of Mars. And then the neural network was able to say, oh, well, hang on a minute. I don't think Earth is the center of the solar system. It seems like there's another center that we are concentrically against. So they want to get fundamental laws of physics. Lamport-Chaton and Baioni and Barbaresco, these guys are focusing on, can I feed in enough integral identities for it to come out, to spit out a new integral identity? I think Lamport-Chaton were able to actually get a couple, which is, this is early days, but we could see that this way of developing. And what I'm hoping, in a way, is now, in some sense, a lot of what I've said here is at the AlphaGo stage, right? We're just doing pattern recognition. And it would be nice to get to the AlphaZero stage of mathematics and mathematical physics, where the actual semantic level you're beginning to understand. We can obviously, even from the syntactical level of understanding the titles of archive, you're beginning to see that this is not entirely impossible. So there's a famous lecture last August by Kevin Buzzard and a panel of the 2018 the International Congress of Mathematics. That's where the Fields Medal panel meet, and they talk about the future of neural network mathematics. And Kevin Buzzard, who is a professor in Imperial, he's actually very optimistic. He thinks within 10 years, all undergraduate theorems in mathematics, undergraduate level theorems in mathematics, will be proved by scratch from computers with no input. So AlphaZero undergraduate level mathematics can all be done. It could be possible. I don't know. It's a very optimistic thing. But this is something that an increasing number of people are actually taking very, very seriously. So thank you very much for your attention.
Thank you. So is there any question, comment?
So I have a question. So certainly it's difficult to ask something in this context. I mean, there's some place where understanding has a different meaning, and well, I got captured by this rare examples of minimal supersymmetric standard models that you mentioned that were so could this machine learning be programmed to find all the MSSM standard models that are?
Yeah, so that's a very good question. So with Rehan Dean and Andre Lucas, we actually with Dean and Lucas and Sanjay Lee, we actually tried exactly this experiment. So in this database that I think Anderson Gray and Palti and Lucas they had something like, if I remember the number, something like on the order of 10 to the 5th exact MSSM models from 10 to the 10 line bundles, right? So now the configuration is very clear. All you need is a manifold, that's a matrix, and the degrees of the line bundles, and that's another matrix. So now just throw it in, and now you may want to do some permutation, enhance the data, make them balanced. And what we did there was, is it possible to get the neural network to start picking out the ones that are MSSM? And that was done, and that you could achieve that in over 99% accuracy. So the ones that are standard model tend to be standard model. Of course, you're looking for something very specific.
Yeah.
And I think similar experiments have been done by Patrick Vodervanker in hydraulic orbifold constructions, and then also by Magdalena Larforce. And I think they're also doing similar experiments. You have these databases from whatever construction that are good models, and there are inherent patterns to good models. Not to say that, of course, that standard model is special. Of course, if you set some other model which have these features that I'm going to label as positive hits, suppose I had 4 generations of particles and 7 Higgs pairs. If I just zoomed in on those, I'm sure the machine would also pick out those as well. So it's unbiased in that sense. But if you feed in enough of the ones and say, this is the standard model, this is a standard model, it's the exact standard model, then that does have its own particular feature.
Okay.
Any other question?
Yes, I have a question.
Yeah, hey.
You mentioned at some point you mentioned a class of questions that involved, say, elliptic curves, or that the Fermat's theorem is this class of problems.
Right.
I wonder if there's any way to use your techniques to throw at the Birch and Swinnerton-Dyer conjecture.
Yeah, that's exactly what we tried. So there are two types of experiments we tried. The first one was the naive one that I did with 2 data scientists, because I'm naive, which was we tried to predict the rank. So the BSD conjecture has, I think, 7 quantities. So there's the weak BSD and the strong BSD, but the strong BSD has, I give you an elliptic curve, you compute 7 quantities, the rank, the tau gamma number, there's a list of these things, and I multiply them together, it should equal to 1, or, after some combination. And I tried to predict the 7 numbers just by looking at the Weierstrass equation, and I got complete crap. So I said, okay, fine, this is a problem. This is an arithmetic problem. Of course, it's hard. But then I got talking to this card-carrying arithmetic geometries. He said, well, don't look at Weierstrass form, because the Weierstrass forms are huge. This elliptic database from the LMFDB database. So the LMFDB database is the Internet L functions and modular forms database. They have 3.5 million elliptic curves, which we downloaded. So that's good. This is the most complete database of elliptic curves. But the Weierstrass coefficients are something like 19-digit integers. So it's huge variation. So these proper arithmetic geometries, well, don't look at them. Look at the L function of these elliptic curves, which has also been tabulated. The L function varies from minus 10 to 10, all the coefficients in the L function when you expand out the Euler product. And then we just took these vectors of these. And then these are kind of coefficients that we get in, accuracy is getting. So, which is great. I mean, so things like the rank of the elliptic curve, we can predict almost 100%. And in fact, we actually did achieve 100%. And so I was excited I can raise a conjecture, that the BSD, the rank of an elliptic curve is this classifier. Luckily and sadly, this conjecture already exists. So this is kind of nice. It's reassuring. I had no idea what it was doing. And I was able to produce this. And that is actually a known conjecture about distribution of these L coefficients in relation to the rank. And what's really interesting is that the Shafarevich group, which is the most difficult quantity in BSD. This is the biggest hurdle to prove in the BSD conjecture, is to compute in this, of the 7 quantities. That one, I could not get more than 0.6% accuracy. So somehow that really is a hard quantity. So that's kind of interesting that, it's kind of intuitively expected. Hard problems are hard and easy problems are easy. Except that, okay, I wouldn't say algebraic geometry is easy, but it's computationally easier than, fundamental problems of primes. I've tried it maybe in a formal sense.
Are you able to like predict? How good are you at predicting ranks? I mean, because there's a conjecture that 100% of all elliptic curves are rank 0 or 1.
Yes, that's right. So what we did is we took 0 and 1 ranks, because the outliers, the higher rank ones are so small, we just drop it. Out of the 3.5 million, we take the 0 and 1 ranks. So can we distinguish rank 0 to rank 1? We know they're 50-50, and then you could distinguish them to 100%.
I see.
And that is consistent with. So I think it's part of the Sato-Tate conjecture that you can tell this. But it's just great that a neural classifier could do this just as well, which is very, I don't know, made us very happy. Made me very happy, especially given the one the Weierstrass coefficients didn't work.
All right. Thank you very much.
Sure.
Okay, I think maybe we should stop here and thank you again.